Good morning, I'm Junbin Kang from Beihang University, and we will present our work, SpanFS, a scalable file system fast storage device. Today's hardware provides high parallelism at every level from manycore processors to memory to fast storage device, such as flash-based SSDs. The high parallelism provided by this advanced hardware is expected to deliver high application-level parallelism. However, the system software deficiencies can underutilize the high hardware performance, especially the poor scalability of file systems can be a bottleneck in exploiting this high hardware parallelism. We set up a simple macro benchmark on a run disk to demonstrate this bottleneck. We use sysbench to generate 4 kilobyte synchronous write to 128 files. Multiple sysbench instances are running in parallel, and we vary the number of instances. In order to show the upbound on performance, we set up an ideal file system by running each concurrent sysbench instance in a separated partition. We can see from the figure the ext4 file system exhibits poor scalability, resulting in nearly horizontal line. The ideal file system achieves near linear scalability, demonstrating that the hardware is not the bottleneck. We also added our SpanFS performance, showing that SpanFS scales much better than the baseline ext4 file system. We also evaluated other model file systems, XFS, BTRFS, and ZFS, of which XFS is a joining file system, and BTRFS and ZFS are copy-on-write file system. The figures show similar results. We concluded that the file systems, whether they are joining or copy-on-write, scale poorly on manycore. In this paper, we focus on the scalability issues of joining file system. We take ext4 JP2 as an example for analysis. We first look into the joining mechanism. Most joining file systems adopt a centralized joining design that first write updates to the single log area and then to the primary area. As shown in the figure, JP2 adopt a group commit mechanism to improve performance. Specifically, there is at most only one running transaction at any time to absorb all updates from applications. The running transaction is committed by the joining thread to the log area, and then put it into the checkpoint list. The wait queues are used to cooperate between joiner thread and the client threads. When there is not enough free space in the log area, JP2 will checkpoint the first transaction in the checkpoint list to make free space. The first issue introduced by such centralized joining design is the serialization of joining activities on device, which can sacrifice high parallelism of SSDs. This is because joining needs to ensure transaction order for correctness due to transaction dependency. As a result, joining performs sequential transaction commits and checkpoints. The second issue is the unavoidable use of shared data structures in such centralized joining design. For example, JP2 uses atomic counters, centralized joining buffer list, and checkpoint list, and wait queues. These shared data structures are frequently accessed and updated during joining, which can cause severe contention on many cores. This table lists the shared data structures used by JPT2, as well as the corresponding synchronization mechanisms. As shown in the table, JPT2 uses read-write logs, atomic operations, spin logs to protect these shared data structures. We use the log statistic tool to confirm this log contention. We can see from the table the JP2 logs are contained severely during the sysbench benchmarking. The total log wait time occupies a significant percent of the total execution time. One question that arises is whether these bottlenecks can be fixed by using parallel programming techniques. The answer and most time is no. For example, JP2 uses read-write lock to protect journal states. Some scalable read-write locks such as RCU and PIW logs. They are scalable for read most workloads, but JP2 has many writes to the shared states. However, the bottleneck of wet queue can be eliminated by using per-core wet queues, but simply removing this bottleneck cannot totally scale file system. We summarized here. Using parallel program techniques cannot fix all the bottlenecks. The centralized journal design introduced two issues: the synchronization of our activities and the use of shared data structures. Hence, we need a new file system structure. Our solution, SpanFS, is to replace the centralized file system service with multiple micro file system service called domains to provide parallel file system service. Each domain has its own on-disk structures and journey instance. During mounting, each domain builds its in-memory data structures from its on-disk structures and starts its kernel services such as the journal thread. As there is no overlap between domains on-disk structures, each domain can perform its journey independently, thus enabling high parallelism for logging, committing, and checkpointing. We also allow block group reallocation between domains to address storage space imbalancing. Although the file system has been parallelized, there still exists a bottleneck beneath the file system layer. The Linux operating system uses buffer cache for each device to cache recently accessed blocks. The two global logs are used to protect the global address space. As a result, when multiple domains access a single underlying device, there may exist log contention. Our solution is to leverage the Linux block device architecture to provide a dedicated buffer cache address space for each domain to avoid such contention. After providing parallel file system service, we then distribute the global namespace among the domains to leverage the parallelism. In order to distribute the namespace, we introduce distributed objects. Each distributed object stores its shared entry and its parent directory, but stores its inode in the remote domain. Then the files and directories and each directory can be distributed among all the domains. However, there exists inconsistency in case of a system crash as the creation spans two domains. The first case is the shared entry is created, but the first case is that the shared entry has been persisted while the inode is lost. Then the shared entry becomes a stale object. The second case is that the inode reach the disk, but the shared entry is lost. Then the inode becomes storage garbage and cannot be reclaimed easily as it is not indexed. Our solution is to build a logical connection between domains beyond the journey. Specifically, we create a remote entry in the remote domain and then build a bidirectional index between the shared entry and the remote entry. We create a set of span directories per domain to store remote entries. Based on the bidirectional index, we propose stale object deletion and garbage connection to address inconsistency. Specifically, SpanFS performs integrity security validation during lookup and read-dir. It removes the shared entries without remote objects. The garbage connection mechanism runs background GC thread in case of system crash. The GC thread deletes the remote objects without shared entries to collect garbage. Another aspect we should pay attention to is the synchronization. As the namespace is distributed, fsync on the target object should guarantee that objects along the file path have been persisted also. Otherwise, it will lead to that the target object becomes the orphan object as the file path has been lost. The orphan object will be collected by GC. One intuitive solution is to iteratively synchronize all the objects along the file path until reaching the root directory. However, the distributed synchronization latency is known. Our solution is to leverage the client-server architecture of GPT-2 to commit the transactions in parallel. The committing phase deliver transaction commit requests to the domains where the file path spans. Then the transactions in these domains will be committed by their joining thread in parallel. In the end, validating phase will check whether each committed transaction has been completed. If not, SpanFS will wait for their completion. It is challenging to achieve atomicity of the rename operation, as the rename operation involves multiple GPT-2 handles across multiple domains. We propose the ordered transaction commit mechanism to achieve rename atomicity. Specifically, we control the commit sequence of the GPT-2 handles. Then system crashes lead to only a small number of inconsistencies. These inconsistency states can be verified online. We implemented SpanFS based on ex4 in Linux 3.18.0. We evaluated SpanFS against ex4 on an Intel 32-core machine with a Fusion SSD. We first begin with a set of metadata-intensive benchmarks. In the create benchmark, each thread creates 10,000 files and is a private directory. X4 performs much better than SpanFS and the create benchmark for two reasons. X4 does not encounter severe contention and this workload, as the create benchmark involves the creation of shared entry and remote entry. This operation introduces some overhead in SpanFS. The append benchmark performs a 4 kilobyte write to each file and then issue a fsync on the file. The fsync in SpanFS will introduce overhead as it needs to span multiple domains to persist file paths. As shown in the figure, SpanFS is slower than X4 and one single core. However, due to better parallelism and reduced contention, SpanFS outperforms X4 by around 1 time and 32 cores. The Truncate benchmark truncates each file to zero size. SpanFS scales much better than X4, and this workload bringing around 7 times performance improvement. The delete benchmark removes all files. SpanFS is around 33% slower than X4 and one core. Due to that, the delete operation involves the deletion of 2 entries in SpanFS. However, SpanFS outperforms X4 by 4 times and 32 cores. The knock contention statistics show that SpanFS largely reduces the knock wait time during the above benchmarking. We use LZone to perform data-intensive benchmark. We can see that SpanFS scales much better than X4 and sequential buffered write, and also sequential synchronous write. we evaluate SpanFS against the X4 using application-level benchmarks, file bench, and dbench, as shown in the figure. SpanFS scales much better than X4, bringing 51% performance improvement and the file server workload. For the one-mail workload, the performance improvement and 32 cores is around 73%. We choose the bench benchmark as it consists of rename, fsync, create, delete operations. It allows us to show the performance impact of the rename operation overhead in SpanFS on a realistic workload. Although SpanFS is slower than X4 and one single core, it outperforms X4 by 16% and 32 cores. We also evaluated the garbage collection performance. The table shows the time taken to scan different numbers of files by GC. We can see that even there exist 3 millions of files in the file system, the GC thread only takes around 20 seconds to complete the scan. We also measure the GC performance impact on the foreground I/O workloads. Specifically, we prepared 3 millions of files and then run the GC thread after remount. Immediately, we run 32 one-mail instances for 60 seconds. The GC thread takes 21 seconds to complete the scan, while meanwhile, the total throughput of the one-mail workload has been degraded by only 12%. It should be noted that the GC thread only runs in case of system crash. Hence, it does not introduce overhead to foreground I/O workloads and normal cases. We present the conclusion here. We present an exhaustive analysis of the scalability bottlenecks of existing file systems. We attribute the scalability issues to their centralized design. First issue is the contention on shared data structures in memory. The second issue is the serialization of journaling activities on device. Then we propose a novel journaling file system SpanFS to achieve scalability on many cores. We demonstrated that SpanFS scales much better than the baseline. Okay, thank you. Any question?
I was curious, this is a sort of detailed question about it, but looking at the talk and the paper, does the on-disk format actually reflect the number of CPU cores that you have available in this implementation? Does the on-disk format change with number of CPU cores?
Does the underlying
format change with CPU count?
What the format means?
Your on-disk format, does it specific to your, like you run it on 4-core, then that's the best on-disk format that you're gonna get with SpanFS. So
the regions on your disk.
Yeah, the regions, the number of regions, and so on.
Okay. I'm sorry.
When you format
yes.
the disk with SpanFS data structures,
yes,
that configuration, does it based on the number of cores that is running at that point? Do you need to specify?
Okay.
Number of cores?
Okay. The number of the domains is set according to the number of cores. But the number of domains is not necessarily equal to the number of cores. In the experiments, we we evaluated SpanFS with 4 domains and 16 domains on a 32-core machine. We can see that even with 4 domains, SpanFS achieves much better scalability as it effectively reduces the contention and bring parallelism.
Okay, thank you.
Thank you.
Right, so Peter has a great question, so leading me to this next question. Can we make SpanFS elastic? Like, can we make SpanFS, you format your disk, it's running on the best configuration, let's say on 4 cores, but now let's say suddenly you suddenly only have 1 core. Can you, be elastic and change your configuration on the fly, maybe future work, something like that?
Okay, good question. Now the number of domains is static. In the future work, we are exploit the dynamic domain creation according to the workload. Yes.
Okay. Right. Let's thank the speaker one more time.
Okay, thank you.